Good morning, everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In the last class, we saw about solving stability problems using matrix method. We will continue to solve more problems for you to enforce the importance of solving stability problems using matrix method. Let's solve a problem using matrix method. Determine the buckling load and buckling mode of a column shown below with constant EI. The left end of the column is fixed, the right end is also fixed, but it allows for axial movement. Recall the governing differential equation for a beam column. V power 4, basically differentiating V 4 times plus alpha square V double dash equal to 0, where alpha square equal to P by EI. The general solution is given as V of x equal to C1 sin alpha x plus C2 cos alpha x plus C3 x by L plus C4. When we differentiate it once, we get V dash of x equal to C1 into alpha cos alpha x minus C2 alpha sin alpha x plus C3 by L, because when you differentiate x, it becomes 1 and differentiate C power 4, basically constant, becomes 0. So when we differentiate twice, we have V double dash of x equal to minus C1 alpha square sin alpha x minus C2 alpha square cos alpha x. We can also differentiate it thrice. So V triple dash of x equal to minus C1 alpha cube cos alpha x plus C2 alpha cube sin alpha x. The boundary conditions are V of 0 is equal to 0. Basically, the lateral displacement is 0 at the starting point of the column, which indicates 0 equal to C1 into sin alpha of 0 plus C2 into cos alpha of 0 plus C3 into 0 by L plus C4, which gives you 0 equal to C1 into 0 plus C2 into 1 plus C3 into 0 plus C4 into 1. Basically, sin 0 is 0, that is given as C1 into 0, and cos 0 equal to 1, which is given as C2 into 1. Which gives rise to the equation 0 equal to C2 plus C4. The next boundary is given as V dash of 0 equal to 0. V dash of 0 indicates the slope at one end of the corner is 0. So, which indicates 0 equal to C1 into alpha into cos alpha of 0 plus minus C2 into alpha into sin alpha into 0 plus C3 by L. So, when we substitute the values, we get 0 equal to C1 into alpha into 1 minus C2 into alpha into 0 plus C3 by L. So, this gives rise to the equation 0 equal to C1 alpha plus C3 by L. The third boundary is V of L equal to 0. Basically, at length L, the lateral displacement is 0, which is given as 0 equal to C1 into sin alpha L plus C2 into cos alpha L plus C3 into L by L plus C4. This can be simplified further as 0 equal to C1 sin alpha L plus C2 cos alpha L plus C3 plus C4. Now, V dash of L is equal to 0. Basically, the slope at the right hand side of the equation is also 0. So, we have 0 equal to C1 into alpha into cos alpha L minus C2 into alpha into sin alpha L plus C3 by L. So, which gives rise to the equation 0 equal to C1 alpha cos alpha L minus C2 alpha sin alpha L plus C3 by L. So, in the matrix form, we can represent that as A into C is equal to 0, where A is given as the matrix, which is given as, I am reading the first row, 0, 1, 0, 1. The second row is alpha 0, 1 by L, 0. The third row is sin alpha L, cos alpha L, 1, 1. The fourth row is alpha cos alpha L minus alpha sin alpha L, 1 by L, 0. Basically, this represents the boundaries, equations 1 to 4. Basically, V of 0 equal to 0, V dash of 0 equal to 0, V of L equal to 0, V dash of L equal to 0. The constants is given as C1, C2, C3 and C4. In the matrix form, A into C is equal to 0. So, A is given as 0, 1, 0, 1, alpha 0, 1 by L, 0, sin alpha L, cos alpha L, 1, 1, alpha cos alpha L minus alpha sin alpha L, 1 by L, 0. C is given as C1, C2, C3, C4. For non-trivial solutions, the determinant of A should be equal to 0. So, when we expand the matrix, we get two 3 by 3 determinants, which is given as minus 1 into alpha 1 by L 0, sin alpha L 1, 1, alpha cos alpha L 1 by L 0 plus of minus 1 into alpha 0, 1 by L sin alpha L cos alpha L 1, alpha cos alpha L minus sin alpha L minus alpha sin alpha L 1 by L is equal to 0. So when we further expand this, we have minus 1 into alpha into 0 minus 1 by L minus 1 by L into 0 minus alpha cos alpha L plus minus 1 into cos alpha L by L minus of minus alpha into sin alpha L bracket close plus 1 by L into minus alpha sin square alpha L minus alpha cos square alpha L bracket close should be equal to 0. In the entire equation, we have minus 1 common so that we can take it out. This gives rise to the equation minus alpha by L plus alpha cos alpha L by L plus alpha cos alpha L by L plus alpha square sin alpha L minus alpha by L into sin square alpha L plus cos square alpha L equal to 0. But we know that sin square theta plus cos square theta is equal to 1. So this becomes minus alpha by L plus alpha cos alpha L by L plus alpha cos alpha L by L plus alpha squared sin alpha L minus alpha by L is equal to 0. This gives rise to the equation 2 alpha cos alpha L by L minus 2 alpha by L plus alpha square sin alpha L should be equal to 0. So when we take this 2 alpha common, we have 2 alpha into cos alpha L minus 1 divided by L plus alpha squared sin alpha L is equal to 0. We can further simplify this by taking it as 2 alpha into cos alpha L minus 1 plus alpha square L sin alpha L by L which is equal to 0. So we have 2 alpha into cos alpha L minus 1 plus alpha square L into sin alpha L is equal to 0. This can be further simplified as 2 into cos alpha L minus 1 plus alpha L into sin alpha L equal to 0. We are basically taking the alpha common and we are reducing the equation further. We also know that cos 2 theta equal to cos square theta minus sin square theta or 1 minus 2 sin square theta or 2 cos square theta minus 1. Here we are using cos 2 theta equal to 1 minus 2 sin square theta. And we are also know that sin 2 theta equal to 2 sin theta cos theta. So it can be written as sin theta equal to 2 sin theta by 2 into cos theta by 2. Using these trigonometric equations, we have 2 into 1 minus 2 sin square into alpha L by 2 minus 1 plus alpha L into 2 into sin alpha L by 2 into cos alpha L by 2 is equal to 0. Again, we can further simplify this. We can take this minus in the previous equation get cancelled. The equation further simplifies as 2 into minus 2 sin square alpha L by 2 plus 2 alpha L into sin alpha L by 2 into cos alpha L by L by 2 equal to 0. Which gives minus 4 sin square alpha L by 2 plus 2 alpha L into sin alpha L by 2 into cos alpha L by 2 is equal to 0. We can take sin alpha L common. We have 2 alpha L into cos alpha L by 2 minus 4 sin alpha L by 2 is equal to 0. Here in this one, either sin alpha L by 2 should be equal to 0 or the brackets, the terms inside the brackets 2 alpha L into cos alpha L by 2 minus 4 into sin alpha L by 2 should be equal to 0. So when we simplify this further, we have 2 alpha L into cos alpha L by 2 is equal to 4 sin alpha L by 2, which gives rise to the equation alpha L into cos alpha L by 2 equal to 2 sin alpha L by 2, which indicates tan alpha L by 2 is equal to alpha L by 2. So the first equation leads to alpha L by 2 is equal to n pi, which indicates alpha n equal to 2n pi by L. For the first mode, which is alpha 1, we have n equal to 1, it becomes 2 pi by L. The second term leads to alpha L by 2 is equal to 4.493. So alpha is equal to 8.986 pi L. So we have to compare the two one and take the one that is least. Here the least value is 2 pi by L compared to 8.986 by L. Therefore, the eigenvalue, the least eigenvalue is alpha L by 2. This leads to alpha L by 2 equal to n pi, alpha n equal to 2n pi by L. As previously discussed, for the first mode, alpha 1 equal to 2 pi by L. The buckling load is given as alpha 1 equal to 2 pi by L, which is equal to P by EI. So P critical becomes 4 pi square EI by L square. For the buckling mode shapes, we have V of x equal to C1 into sin alpha x plus C2 into cos alpha x plus C3 into x by L plus C4. So the determinant of the matrix is given, which we have previously discussed, 0, 1, 0, 1, alpha 0, 1 by L 0, sin alpha L, cos alpha L 1, 1, alpha cos alpha L minus alpha sin alpha L 1 by L 0. C is given as C1, C2, C3, C4. Substituting alpha n equal to 2n pi by L, we have 0, 1, 0, 1, alpha 0, 1 by L 0, which is the same as the previous one. But here, instead of alpha L, we put 2n pi by L, which gives sin 2n pi, cos 2n pi, 1, 1. The next row, the last row, is alpha cos 2n pi minus alpha sin 2n pi, 1 by L 0, which can be further simplified as 0, 1, 0, 1, alpha 0, 1 by L 0, 0, 1, 1, 1, alpha 0, 1 by L 0. These are the 4 rows, and multiply by C1, C2, C3, C4 is equal to 0, 0, 0, 0. Now, this can be further simplified when we multiply both the matrices. We get C2 plus C4 is the first row, alpha into C1 plus C3 by L is the second row, C2 plus C3 plus C4 is the third row, and alpha into C1 plus C3 by L is the fourth row. So this can be equated to the equation on the right side, basically the constants 0, 0, 0, 0. This becomes 1, 2, 3, and 4. We can independently solve all these equations. So solving equation 1 leads to C2 equal to minus C4. Solving the third one, we get C2 plus C3 plus C4 is equal to 0. Since C2 equal to minus C4, C3 becomes 0. Solving the fourth one, we get C1 equal to 0. So we can substitute the values of C1, C2, C3 in the equation. V of x equal to C1 sin alpha x plus C2 cos alpha x plus C3 into x by L plus C4. So when we substitute the buckling mode shape, we get this V of x equal to C2 into cos alpha n x minus C2. Again, we can take that as constant. Since we have only one constant, C2 can be turned as C, and we take the C common. We have C into cos alpha n x minus 1, alpha n equal to alpha 1, first mode equal to 2 pi by L. So V of x equal to C into cos 2 pi by L into x minus 1. Now, let's look at problem 2. Determine the buckling load and buckling mode of a column shown below with constant EI. The left end of the column is fixed. The right end of the column is supported by a linear elastic spring whose stiffness is K. The length of the column is L. It is subjected to an axial compressive force P. Recall the governing equation for beam column. We have V 4 times differentiation, which is V dash 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 plus alpha square into V double dash is equal to 0, where alpha square equal to P by EI. The general equation is given as V of x equal to C1 sin alpha x plus C2 cos alpha x plus C3 into x by L plus C4. So V dash of x is given as C1 alpha cos alpha x minus C2 alpha sin alpha x plus C3 by L. V double dash of x equal to minus C1 alpha squared sin alpha x minus C2 alpha squared cos alpha x. We have V triple dash of x equal to minus C1 alpha cube cos alpha x plus C2 alpha cube sin alpha x. Now the boundary conditions are the slope and deflection at x equal to 0. So V of 0 is equal to 0. So when we substitute it, we get 0 equal to C1 sin alpha 0 plus C2 cos alpha 0 plus C3 into 0 by L plus C4, which gives rise to the equation 0 equal to C2 plus C4. The second boundary condition is slope is 0, which is V dash of 0 equal to 0. So when we substitute it, we get 0 equal to C1 alpha cos alpha 0 minus C2 alpha sin alpha 0 plus C3 by L, which indicates 0 equal to C1 into alpha plus C3 by L. Moment at x equal to L is 0. So V double dash of L is equal to 0, which gives rise to the equation 0 equal to minus C1 alpha square sin alpha L minus C2 alpha square cos alpha L. So we have 3 equations, but we have 4 unknowns, C1, C2, C3 and C4. So how do we get the fourth equation? For the fourth boundary conditions, we know that V equal to minus d by dx of EI into d square V by dx square minus P into dV by dx. Right? We have solved this one previously in the development of beam column equations. So we are going to recall this value and then we have to proceed with this. So we have V equal to minus d by dx of EI into d square V by dx square minus P into dV by dx. So V of L at length L is minus d by dx of ei into d square v sub L divided by dx square minus p into d of v sub L divided by dx. From the force displacement relation of linear spring, we have F equal to minus kx, which indicates V of L equal to minus k into V of L. So we can substitute that in the above equation. Minus k into V sub L equal to minus ei into V sub L triple dash minus p into V dash L. So we can substitute this value in the above equation. We have minus k into C1 sin alpha L plus C2 cos alpha L plus C3 plus C4 is equal to minus ei into minus C1 alpha cube cos alpha L plus C2 alpha cube sin alpha L minus p into C1 alpha cos alpha L minus C2 alpha sin alpha L plus C3 by L. So now what do? We divide with the both sides of the equation with ei. We get minus k by ei into the same equation is equal to minus ei by ei, the same equation, minus p by ei, and whatever the equation that is there in the bracket, the green color equations. So let's also term k naught equal to k by ei and alpha square equal to p by ei. So when we do so, we get minus k naught into C1 sin alpha L plus C2 cos alpha L plus C3 plus C4 on the left hand side is equal to minus of minus C1 alpha cube cos alpha L plus C2 alpha cube sin alpha L minus alpha square into C1 alpha cos alpha L minus C2 alpha sin alpha L plus C3 by L. So this can be further simplified as minus k naught C1 sin alpha L minus k naught C2 cos alpha L minus k naught C3 minus k naught C4 is equal to C1 alpha cube cos alpha L minus C2 alpha cube sin alpha L minus alpha cube C1 cos alpha L plus alpha cube C2 sin alpha L minus alpha squared C3 by L. We have terms that can be cancelled, as you can see from the equation. So when we simplify this further, we have minus C1 into k naught sin alpha L minus C2 into k naught cos alpha L minus k naught C3 plus alpha square into C3 by L minus C4 k naught is equal to 0. So this can be further simplified as we have all the equations in terms of minus C1 into k naught into sin alpha L minus C2 into k naught into cos alpha L minus C3 into k naught minus alpha squared by L minus C4 into k naught equal to 0. Since the minus is constant or minus is common for the equation, which can be further simplified as C1 into k naught sin alpha L plus C2 into k naught cos alpha L plus C3 into k naught minus alpha square by L plus C4 into k naught is equal to 0. This can be further simplified by dividing this entire equation by k naught. We have C1 into sin alpha L plus C2 into cos alpha L plus C3 into 1 minus alpha square by k naught L plus C4 is equal to 0. So we have now the fourth equation for which we can have a matrix. So if we put it in the matrix form, A into C is equal to 0. So the matrix A is 0, 1, 0, 1, alpha L 0, 1, 0, sin alpha L, cos alpha L 0, 0. The fourth row is sin alpha L, cos alpha L, 1 minus alpha square by k naught L and 1. C is given as C1, C2, C3, C4. For non-trivial solutions, the determinant of A should be equal to 0. So when we expand it, we have minus 1 into alpha L 1, 0, sin alpha L 0, 0, sin alpha L 1 minus alpha squared by k naught L into 1. And the next one, which is shown in the green color, when we expand it, we have minus 1 into alpha L 0, 1, sin alpha L cos alpha L 1 minus alpha squared by k naught L is equal to 0. This can be further simplified as minus 1 into 0 minus sin alpha L and plus minus 1 into 1 into sin alpha L cos alpha L minus sin alpha L cos alpha L plus 1 minus alpha square divided by k naught L into alpha L into cos alpha L is equal to 0. The terms sin alpha L and cos alpha L gets cancelled. We can simplify this further. We have sin alpha L minus of bracket open 1 minus alpha square divided by k naught L bracket close into alpha L cos alpha L is equal to 0. So we have this equation which we have simplified. So we have further simplification to be made. So sin alpha L is equal to 1 minus alpha square divided by k naught into L into alpha L into cos alpha L. So we can represent this as sin alpha L by cos alpha L is equal to alpha L into 1 minus alpha square by k naught L. So when we simplify this equation further, we have tan alpha L equal to alpha L into 1 minus alpha square divided by k naught L. So if you look at this column we have one end of the column which is fixed, the another end of the column is resting on a linear spring whose stiffness is k. So if the end of the column was simply supported, we have k tending to infinity, which means that k naught also tends to infinity, which gives rise to this value alpha square divided by k naught L tends to 0. So if the end was simply supported, tan alpha L equal to alpha L, which means that root of P critical by EI into L is equal to 4.493. When we simplify this further, we have P critical by EI into L square is equal to 2.046 pi square. So P critical becomes pi square EI by 0.7 L the whole square, which is identical with the fixed and pinned columns. What if the K has a different value? So if the ends was free, K is tending to 0. So if K tends to 0, K naught also tends to 0. If K naught tends to 0, 1 minus alpha square by K naught into L is equal to infinity. If the ends was free, so tan alpha L equal to infinity. So alpha L equal to n pi by 2. So if we simplify this further, we have root of P critical by EI into L is equal to n pi by 2. So we have P critical equal to n square pi square EI by 4L square. So this is identical with the fixed free columns. Let's look at another problem, problem 3. Here, instead of a linear spring, we have a rotational spring. So the problem is determine the buckling load and buckling mode of a column shown below with constant EI. Recall the governing differential equation for a beam column. We have V differentiated 4 times plus alpha square into V double dash is equal to 0, where alpha square equal to P by EI. The general solution is V of x equal to C1 sin alpha x plus C2 cos alpha x plus C3 into x by L plus C4. V dash of x equal to C1 into alpha cos alpha x minus C2 into alpha sin alpha x plus C3 by L. V double dash of x equal to minus C1 alpha squared sin alpha x minus C2 alpha squared cos alpha x. When we differentiate it thrice, we have V triple dash of x equal to minus C1 alpha cube cos alpha x plus C2 alpha cube sin alpha x. So the boundary conditions are the deflection at x equal to 0 and x equal to L is equal to 0. So V of 0 equal to 0, which indicates 0 equal to C2 plus C4, which we have seen previously. So V of L equal to 0, which means that 0 equal to C1 sin alpha L plus C2 cos alpha L plus C3 plus C4. Moment at x equal to L is 0, which means that V double dash of L is equal to 0, which indicates 0 equal to minus C1 sin alpha L minus C2 cos alpha L. So we have 3 equations but 4 unknowns, C1, C2, C3 and C4. So how do we find the fourth equation? So let's look at this plot here. We have the deflected shape due to the buckling. So we have at point A, the deflection is given as V, which is at the distance x from the left hand side. So for the fourth boundary condition, the applied moment is m sub s equal to s into theta. So the theta equal to V dash of 0 at x equal to 0. So the internal resisting moment is mi. So when we take the equilibrium, we have mi plus ms is equal to 0. Mi is given as minus Ea into d square V by dx square and ms is s theta. So we have minus Ei into d square V by dx square plus s theta is equal to 0. So minus Ea into V double dash of 0 plus s into V dash of 0 is equal to 0 because slope is given as V dash of 0 at x equal to 0. So this gives rise to the equation minus Ea into minus C2 alpha square is equal to minus S into C1 alpha plus C3 by L when we substitute the value of B equal to 0 in the above equations that we have derived. So we have alpha into S into C1 plus alpha square EI C2 plus S by L into C3 is equal to 0. So we have 4 boundary conditions and we can express this in the matrix form A into C is equal to 0, where A is given as 0, 1, 0, 1, sin alpha L, cos alpha L, 1, 1, sin alpha L, cos alpha L, 0, 0, alpha S, alpha square EI, S by L, 0. C is given as C1, C2, C3 and C4. So for non-trivial solutions, the determinant of A should be equal to 0. So when we expand this one, we get this equation minus 1 into sin alpha L 1 1, sin alpha L 0 0, alpha S S by L 0. Next, we have minus 1 into sin alpha L cos alpha L 1, sin alpha L cos alpha L 0, alpha S alpha square EI S by L is equal to 0. So we expand this further. We have minus 1 into S by L into sin alpha L minus 0 plus of minus 1 into sin alpha L into S by L into cos alpha L minus 0 minus cos alpha L into S by L into sin alpha L minus 0 plus 1 into alpha square EI sin alpha L minus alpha S cos alpha L equal to 0. This can be further simplified. As you can see below, both the equations can be simplified further by cancelling few terms. So we have minus S by L into sin alpha L minus alpha square EI into sin alpha L minus alpha S cos alpha L is equal to 0. So this again can be further simplified as shown below. We have S by L into sin alpha L plus alpha square EI sin alpha L minus alpha S cos alpha L is equal to 0. So multiplying the both sides of the equation with minus L by S further simplifies this equation. So when we do so, we have sin alpha L plus alpha square L EI divided by S into sin alpha L minus alpha L into cos alpha L is equal to 0. So when we take the sin alpha L common, we have sin alpha L bracket open 1 plus alpha square L EI by S bracket close equal to alpha L into cos alpha L. So we can take the term inside the bracket to the right hand side and the term here cos alpha L to the left hand side. We have tan alpha L is equal to alpha L divided by 1 plus alpha square into L EI by S. So for simply supported conditions, S tends to 0. So in the equation, when we substitute S equal to 0, we have 1 plus alpha square L EI by S tends to infinity, which indicates that 1 by the same term, which is alpha L divided by 1 plus alpha square L EI by S tends to 0, which indicates that tan alpha L equal to 0, alpha L equal to n pi, which gives rise to the equation P critical equal to n square pi square EI by L square, which is identical to the previously derived pin-ended columns. Now what happens when we have for fixed condition, the spring stiffness tends to infinity. So we have tan alpha L equal to alpha L divided by 1 plus alpha square LEI by S. So when S tends to infinity, 1 plus alpha square LEI by S tends to 1, which indicates that tan alpha L equal to alpha L, which gives rise to the equation P critical equal to pi square EI by 0.7 L square. This is identical to the fixed pinned columns that we have derived previously. So with this one, we have fairly understood that Martix method can be very helpful to determine the buckling coefficient for linearly varying spring as well as rotational springs. So this gives a fairly good idea that real life structures do not have very definite boundary conditions. The boundary conditions vary with respect to the beams and columns that are adjoining the connection at that location, based on which the K factors will be derived. And this is an indication of how we can solve this one without going into complex mathematics of partial differential equations or ordinary differential equations to solve problems. So this Martix method can be very helpful in arriving at the K values without getting involved in differential equations for solving problems whose stiffness is not definite, whose stiffness or the end conditions varies with respect to the linear spring as well as the rotational spring. We will continue our conversation on stability in the next class. Thank you very much.